Hello, and welcome to the Mariles Group. I'm sure you remember from your intro courses that among the observations that led to quantum mechanics were absorption and emission experiments in atoms from dilute gases and vapors. For example, researchers at that time used discharge lamps to excite these gases and observed bright lines at well-defined wavelengths that then they associated with the discrete energy levels of the atoms. Now imagine the possibilities if you could trap these atoms in a solid at fixed locations. Even more, imagine you can look at these trapped atoms one at a time. Well, in practice it turns out one can get now pretty close to this scenario if one considers the individual impurities or other types of defects in crystals, each of which occupies just one or a few lattice sites. Similar to the atoms of a gas, these systems have well-defined discrete energy levels that can be excited selectively without disturbing the other atoms forming the host crystal. In other words, the host crystal is totally transparent and the experimenter interacts directly with these defects. The experiments in our group were presently focused on this class of systems. From the many types of defects one can imagine, we're interested in those having an internal angular momentum or spin. A defect we look at extensively is the so-called NV center in diamond, which is formed by a nitrogen atom taking the place of a carbon atom and sitting immediately adjacent to an empty lattice site or vacancy. In our experiments, we routinely combine magnetic resonance and optical microscopy to manipulate and detect the spin state of individual NV centers, which is the equivalent of interacting with atoms just one at a time. Now you wonder, why is this interesting? Well, it turns out there's a broad range of fundamental problems and practical applications of quantum mechanics that one can imagine and realize. For example, you can mount a nanocrystal hosting a single NV center on the tip of an atomic force microscope and use it as an atomic probe to go and sense other spins. The result is a form of magnetic resonance imaging, or MRI, with nanoscale resolution. Because the properties of these defects also depend on temperature, the same setup can be used as a local thermometer to reconstruct temperature maps of integrated circuits, for example, with nanometer precision, or to measure related properties like thermal conductivity in heterogeneous samples. Perhaps more interesting, imagine you create an array of these defects in a bulk crystal and find a way to communicate these separate defects, for example using photons or charge carriers, to create a quantum network. This idea could serve as a platform for a new class of computers, the so-called quantum computers, which can outperform classical computers in many ways. The experiments we do in our group tackle these related areas with a range of techniques that combine ideas from magnetic resonance, atomic physics, and quantum control, and use state-of-the-art experimental tools and nanofabrication techniques. We have assembled a series of short clips that will tell you more details on our ongoing work. So now relax, sit back, and enjoy.